Hello everyone. I welcome you all to the week 4 problem solving session of Ultrafast laser spectroscopy. In the past we three modules, what we have learned is the different types of techniques which are used for the ultrafast laser spectroscopy. That included TCS/PC, fog techniques, and etc. and many more. Now in this session this session covers most of the properties related to laser and how the phenomenon of the lasing occurs. Related to this, here we'll be discussing the questions as we have done in the previous modules. First, without wasting time, since I have been waiting for the people to come, I assume how many people are there. Okay, so no one has joined yet, but without any delay, I would prefer to continue, to not wait and just start the session. So, uh, so first of all, I'll be sharing my screen so that in case anyone comes, he may know. Yeah. This is the session 4 for problem solving, and without any delay, we'll go with the first question. The question 1 is stimulated and spontaneous emissions, respectively. The options to this question are coherent and incoherent, omnidirectional and unidirectional, unpolarized and polarized, and polychromatic and monochromatic. So, first of all, in order to explain this, I'll go with like what is stimulated and what is a spontaneous emission. Okay, what is a stimulated emission? As the name suggests, suppose I consider a system like this. Okay, yeah. So for this I need to take a pen. Uh, yeah. So, what does the term stimulated mean? So, stimulated means something which is initiated by a stimuli, okay, which needs some external, you can say something, a stimulus or a disturbance, so that it can emit. Okay, so actually everything is within the name only. Suppose I consider a system in which the molecules are in the ground state 1 and the other excited state I consider to be 2. Okay, now there are different types of emission. Spontaneous emission, the example would be like if the system is in ground state, it gets excited to the this particular second excited state, and then after that it comes to the ground state by emitting the light radiation. Okay, so that type of emission will be called as a spontaneous emission. But in the stimulated emission, suppose I consider the system where this is the ground state, this is the excited state. So there is a photon of certain energy which is equal to h, which is equal to nu 12. Okay, so this system absorbs that nu 12 amount of energy, which is equal to the energy gap between these two energy levels, and it reaches to a higher excited state. Okay, 2. Now this type of since this going from a ground state to an excited state, this process is called as the absorption. Okay, and since this absorption is taking place with the help of some photon of light, so it is called stimulated absorption. Okay, so this is not like a normal absorption. We need a photon, like actually any kind of absorption, we need to give it an external input of energy for the absorption. So this type of absorption will be called as stimulated absorption. Now similar to this, if you reverse this process, now consider this is the ground state 1, this is the excited state 2. Okay, now you have some molecules, although according to the Boltzmann law, it will never be a condition that N2, that means the population of N2 will be greater than N1. So this happens never. Always in each and every case, n1 will always be greater than n2. Okay. Now, suppose you just incident it with some frequency of light and your system gets excited to a higher energy state. Okay, this is 2. Now, in this case, we are talking about emission. So, with the help of some external stimuli, which is an energy of h nu, this second from the excited state with the help of emission of radiation, the system comes to the ground state. Okay, so the amount of energy that, or you can say the photons are released as a part of this emission process. So this is called as the stimulated emission, which states that there is some sort of some kind of stimuli which is needed for the system to come to the ground state by emitting the radiation. So basically, when you talk about stimulated emission, you talk about the thing laser. Okay. And what is this laser? This laser has the full form of light amplification and stimulated emission of radiation. Okay. Now, this is the full form of laser. When we talk about the stimulated emission, within the name of laser, you may get to know that laser is something related to the stimulated emission. Okay. Now, the specifications or the qualities of a laser that we had studied in the week 1 module, that the laser has the light which is emitted from the laser, it is first of all, it is monochromatic. Okay. The second thing was it is coherent. Coherent refers to all the wavelets which have formed that wave packet that are in the same phase. There is no difference in the phase of each wavelet, and therefore they are called to be coherent. And if you want to see it to be practically, just the lasers which we normally use daily, if you see it, all the wavelets, if they form a circle, when you just switch on the laser and face it towards the wall, that you will see in the form of the uh, circle itself. Like there will be no like you can say the spreading of the spot. So that thing is called the, it is highly collimated. Okay. And the fourth point for the laser is the fourth point for the laser is fourth, it is highly polarized. Okay. So the light beam that comes out of laser is polarized, and that too in it is not at all unpolarized, and that too in the same direction. Okay. Now suppose the light beam which you incident as a light source for the for laser light, if it is in this direction of polarization, when it comes out, the polarization would be the same of the output beam. It would not change. So this is also one important property of the laser. If the input beam is in this direction of polarization, the output beam will also be in the same direction of polarization. But unlike this, the spontaneous emission, which includes some emission like is fluorescence, or in a normal case, when you do not need any stimuli as for the emission, then it is called to be a spontaneous. It does not need any driving force to occur, and that's why it is called as the spontaneous emission. So in our question, our answers were the stimulated and spontaneous emissions respectively are coherent. Now talking about stimulated, yes, the stimulated is coherent, and the spontaneous emission, it will never be coherent. It is incoherent. So maybe in this question this answer can be correct, but for the knowledge purpose we need to discuss these three options as well. So if we are talking about omnidirectional and unidirectional, what does this term omnidirectional means? Omnidirectional means suppose we are the light beam propagates in this direction, it will not be in this direction, it can spread as well. So this is similar to something what we talked about collimated. So stimulated emission, as I told, is never omnidirectional. It is always like a straight beam of light. Therefore, the stimulated beam will always be unidirectional and not omnidirectional. Okay. So basically, for stimulated, if they're talking about the thing respectively, stimulated is not omnidirectional and spontaneous is not unidirectional. So this option will be incorrect. Then the third is unpolarized and polarized. This point also I have discussed already, that the stimulated beam or the stimulated emission, it has a polarized light, and that too is polarized in the same direction. That is the input beam and the output beam. Both of the beams will be polarized in the same direction only. The direction will not even change. And talking about the spontaneous emission, they are unpolarized. So this option also does not go with our uh, uh, like the question. The fourth option is polychromatic and monochromatic. What does the term polychromatic means? The polychromatic term means that the light beam, it does not possess the like the same wavelength of light. It possesses different wavelengths of light. Maybe if you what you see is a blue, maybe if you see it to be a blue light, it may be a mixture of 400 to 500 nanometer. Okay, but if you see the laser of a blue light, that will be exactly either 400 or 420 nanometer. That will be the exact same. Okay, so means if you're talking about a 400 nanometer laser, it will be exactly 400. It will not contain a mixture of 400 to 500 or 600. Okay. So on the other hand, the spontaneous emission, it is polychromatic. Okay. Means it has a mixture of wavelengths. So basically, we come to the conclusion that in these options the term coherent and incoherent goes with our is the right option amongst all. Why? Because the other three are like they have just got exchanged in the choices. Okay, so now if any one of you, I think no one has joined, but I'll proceed with the other question. In case few persons join, after some time, we can discuss this question next time. Now we come on to the question number two. The correct statement among the following about Einstein's coefficient is. Okay. So first of all, actually in this question there are very less details given. So we'll be discussing we'll start from the beginning. We'll see what this A1, A2, B12 and B21 are. So as I stated in the previous question, we had drawn a system where say this is the ground state. Okay. Yeah. So this is the ground state 1, and this is the excited state 2. There can be different cases. The first one is because since without absorption no emission will not take happen. So first of all, with the help of source of energy, it reaches to a higher energy state. Let's say it absorbs the energy of nu 12. It reaches to a higher energy state. This process is called as absorption. Okay. The second process is this. The second process is when it go reaches to a high state, it with the help of a stimuli, say in the form of a photon itself, it reaches to a ground state by emission of radiation, say h nu 2, because this has a will have a different frequency. So this will call to be as emission. And the fact about the two are, since they are using any stimuli as the driving force, so they are will be called as stimulated absorption and stimulated emission. Now, along with this, there is also a third process that happens along with the emission called stimulated emission, that is from 2 to 1. It will return with the emission of radiation, but it will not use any external stimuli. The process in which there is no external stimuli used, it is called as the spontaneous emission. Okay. Now, talking about this spontaneous and stimulated emission, there may be a question in a system whether all these processes occur simultaneously. So, first of all, the answer to this is absorption occurs anyway. Okay, so the first step, absorption will occur for a system, but these two processes, spontaneous and stimulated processes, first and the second, they both also occur simultaneously. It is not like that only stimulated emission occur and the spontaneous does not occur. Both the processes will occur simultaneously. Now, so what was the Einstein's approximation? His approximation was that he prepared a kinetics equation for the stimulated emission. So that is called as wait, I'll write this entire thing on a blank page, and then it will be more clear, and will have more space also. So we'll discuss the Einstein's kinetics for stimulated emission. Okay. So hi Rahul, I assume you are the first one to join this session. Would you like to introduce yourself?
Hello.
Hi Rahul.
Yeah.
Okay, actually, we have done one question. We have solved one question till now. So, if you want, I can repeat that question in a
No,
short.
I think I have a doubt in the. This is assignment 4, right?
Yes, yes.
Yeah, I have doubt in question number 4. So
Okay, question
question number
number.
1 is 4.
Okay, this one.
Yeah.
Okay. So, since I'm proceeding with question number
Yeah,
two,
yeah. You can. Yeah, I'll wait for that.
yeah, okay, sure.
Okay. Thank you.
Yeah, so we were discussing Einstein's kinetics for stimulated emission. So, what he assumed was, just a second. Yeah. So this is a ground state 1 and this will be the excited state 2. So there are three processes going on at the same time in the system. So first one was a system absorbs certain frequency of light nu 1 to reach to a higher energy state. This is the excited state and this is the ground state. Okay. The second, so this process where it absorbs a beam of light, that is called the stimulated or simply absorption. So it is called as stimulated absorption. The second one will be like, suppose first of all, this is called stimulated because in a photon of light is used to excite the system from ground state to the excited state. And the point to remember is the photon should have the same frequency equal to, or same frequency or a greater frequency than the energy gap between the two states. The second step, which is a new process, or which is the main topic of discussion, is the stimulated emission. Okay, so with the help of a stimulus or a disturbance in the system, sorry, a stimulus means an external factor, that is a photon. The entire excited state, it comes to the ground state by emission of radiation, and that is why it is called as the stimulated emission, right? And the third process will be without any external stimuli from excited state 2 to 1, it will return to the ground state, and that process is called spontaneous emission. Yeah. So, in order to describe the entire kinetics, there are two factors on which this stimulated emission depends, okay, and excitation as well. So, the first one is the population of the ground state. Let's say the population of the ground state is N1 and the excited state is N2. Now, since this is a system where the molecules are confined to N total, although this will come later, but we'll take that the total population is constant and we'll take it to be N total, and that will be the sum of N1 plus N2. That means the population of, that means the sum of population of ground state and the excited state. Okay. Now, what we want to discuss is that what now suppose you write the equation of kinetics, say A gives B, you always write it that the rate will depend on, is equal to the rate constant K multiply by the concentration of the, like, A, because only the concentration of A is the factor that will affect the rate. Now, in this case, for the absorption, what are the factors that will affect is the energy of photon, and second is the population of ground state. So, for the absorption, I'll write it in short, ABS. The thing that, or the factors that vary are, first of all, it is the population N1. The second factor is the energy density rho, which we write as rho 1 to mu. Okay, and the constant which will be taken as B. Okay, so this is what they asked in the second question, that was Einstein's coefficient for stimulated absorption and stimulated emission. So since the system is reaching from 1 to 2, we'll call to be it to be as B12. Got it? Now, similarly, for the stimulated uh, emission, the rate will be N2, since this is the state from where the emission will occur. Similar to this, the energy density of photon, that is rho 12, and the other thing, the rate constant will be B21. Okay. Now the third thing is for the spontaneous emission, what he assumed was, for the spontaneous emission the rate constant will be A. Okay, and since it does not require the factor of photon, so this energy density rho thing which we will not write in this case, so it only depends on the population of N2, and it will be written as A21 N2. Got it? Now these three are the things that are working, and what do we consider? We'll consider the steady state approximation, like the rate of for in steady state approximation. Normally what we consider, if A is going to B and B is going to P, where B can be taken as the intermediate, the rate of formation is equal to the rate of deformation. Okay, so what is the, in this case of the entire thing, for absorption and emission, only the absorption is the thing that is working in, like from N1 to N2, the other two are the reverse processes of that. Okay, so we'll write an equation where we'll write as, in the steady state approximation, the overall rate will be 0. So first of all, what we'll write, this equation 1, this equation as 2, and this equation as 3. Okay, so the net rate or the net difference is 0. So we'll write B12 multiplied by N1 multiplied by row 1 to new is equals to B21. Actually, in order to explain the entire thing, I need to give this small introduction sort of thing. Row 1 2 into new plus A21 N2. Okay, since this page is over, I'll go to the on to the next page. What we had written on that page is B12 N1 into row 1 2 new is equals to B21 N2 row 1 2 new plus A21 into N2. Now we have to I'll just bring these two terms with row common on the LHS, so it will be written as B12 N1 row 1 2 into new is equals minus B21 N2 row 1 2 into new is equals to A21 N2. Got it? And now I'll take common this row 1 2 out new, and in the bracket I'll write B12 N1 minus B21 N2 and is equals to A21 N2. Okay. Now row 1 2 into new is equals to A21 N2 whole upon B12 N1 minus B21 N2. Is it right? Yeah. So this is now what I just want to do is there is a thing, this A21, that is for the spontaneous emission, and B12 and B21 for the stimulated absorption and emission. Okay, now actually what we want to come to the conclusion is, here they were talking about this, and the correct statement among the following for the Einstein's coefficient is. Now, A12, as I mentioned there, A12 denotes the spontaneous emission, and B12 and B21 they denote the stimulated absorption and emission. Then, how do we deduce this relation and what is the relation? So, which we'll conclude this from a different equation. Actually, there is one more equation for the energy density, that is rho 1 2 nu is equal to 8 pi h nu 1 2 whole cube upon c cube bracket e to the power h nu upon kb into t minus 1. Okay, now actually what I'll do is compare, when you compare this equation to this equation, you will get some things new. Okay, so first of all, let me bring this up. Okay, so then only we'll be able to compare. And the second thing is e to the power h nu kbt minus 1. Now this thing what we have got is b12 n1 and b21 n2. Now we want some 1 in this case. Okay, so in order to make it 1, I'll just divide it whole by b21 n2 upon b21 n2, and here I'll also divide by b21 n2. Okay, now this will become 1, and therefore I'll write it as a21 n2 by n1 whole upon b21. Okay, and this will come to be b12 upon b, array, oh just a second. Okay, I'll write it on the top side. So it will come to be A21 upon B21 into N1 by N2, sorry, N2 by, okay, I think that is N2, yeah. So here was, yeah, this one was N2 only, and this is not N2, this is N2 by N2, okay. And then in the denominator side, it will be B12 by B21 N1 by N2 minus 1. Got it? Now this n2 and n2 will be cancelled, and a21 upon b21 whole upon b, well, let's say I'll write it b1 by b2 into n1 by n2. Okay. Now when I compare this whole thing, e to the power minus h nu by kbt and b1 by b2 e to n into n1 by n2, and what I have done here is 8 pi h nu by c whole cube. I have written this entire thing in numerator. Now this the other thing is, uh, n1, since it is greater than n2, and you can say e to the power h nu by kbt. So we'll just compare it with this equation. I'll go to the next page. So in this equation, what we had got is, yeah, we want to okay. So yeah, so b12 by b21. Now I am only considering the denominator into n1 by n2 minus 1 is equals to e to the power h nu by kbt minus 1. Now, as you know, this n1 by n2 from that Boltzmann rule, what we consider, is equal to h nu by kbt. So, here comes, since this e does not have any that term here, so we'll consider like it is to be 1. So it will come to be b12 upon b21 is equals to 1, which states that b12 and b21 are same. Okay, they have equal value. So b12 is equals to b21. Okay, so this is the relation what we have got so far. And here half of the part of our question is solved. So the first thing was, since in the option we have given we are given different options. So the first one, b12 and b21 are equal. This part we have solved. Now we'll come to the numerator portion. Okay, a21 upon b21. Okay, so now I'll write it simply as a upon b. Got it? So a upon b, and what was the value? The value was 8 pi h nu by c. 8 pi h nu by c whole cube. Okay, and since c upon nu is equals to lambda, we can say it nu by c is equals to 1 by lambda is equals to nu bar, which is the wave number. Is there any doubt in the solution so far? Is
No, no.
Okay, thank you. Now, since all these values are constant and this value is also not negative, wave number will have some positive value, which states that a upon b should be some positive value which should be greater than 1. Now, if a upon b value is greater than 1, definitely a should be greater than b. Uh, is it correct? So in any case, if you consider, the value of A should be greater than B. Got it? Okay. So I assume there is something wrong in one of the options. I think this option was like somewhere I just wrongly typed the answer. Okay. The correct statement among the Einstein's coefficients would be, first of all, B1 and B21 will be equal. So where is the option this and A12? Okay. But if you want to consider a stimulated emission, so in an ideal condition, what they are asking, in an ideal condition, the for stimulated emission to occur, the value of B should be greater than A. So according to this, they have told that this will be the correct option. Okay. But practically, A will be greater than B. Okay. Now in this whole solution, do you have any doubt?
No.
Yeah, okay. So I'll go on with the third question. Question number 3 states, uh, you have patented a new gain medium for lasers using vibranium energy level diagram shown below. And the output wavelength is 496 nanometer. Which of the following transitions is responsible for the output light? Okay. So first of all, this energy level diagram they have given to you, where E1, E2, E3, E4 and till En there are the various energy levels, and E1 has the energy of minus 8 electron volt, and the output wavelength, what the output means the emission wavelength is, they have told it to be 496 nanometer. Now, so they are just asking that which transitions among the following is responsible for this, whether it is minus 8 sorry minus 4 to 8, or minus 1.5 to 4, or minus 1.5 to 8, which of those. So first of all, we have to compare the energies. If the energy gap between the two levels matches the output wavelength, then we can say that this particular transition is only responsible for the output light. So, what are the things we are given? The wavelength of output light. From this, we can calculate the value of energy using the equation. And the second is the transition. But the problem here is each of the value is given in electron volts. And the energy difference between the two levels we have to calculate. So basically, I'll just suppose the transition is happening, or the output wavelength is from this to this level, that is E2 to E1. So first of all, I'll calculate the delta E. The delta E would be E2 minus E1, or okay, since the energy of E1 is higher, so we'll just write minus 8 plus 4 electron volt. And how did I do this to be plus? Because this was minus and this was minus, it turned out to be plus, and therefore the energy difference would be 4 electron volt. Okay. Now the energy difference between E1 and E2 is 4 electron volts. I'll solve this question on a fair page, on a clear page. Minus 84 minus 1.5 and minus 1.3. So here the energy levels they had drawn. This was minus 8.0, minus 4.0, minus 1.5 and minus 1.0. I assume these I have written correct. So the question is very easy. You have to just compare the value of the energy difference with that of the energy of that wavelength emitted. Sorry, energy of that emitted wavelength of light. Sorry, energy of that emitted light. So first of all, what I did was E1, E2, E3 and E4. First I did E2 minus E1. It came out to be 4 electron volts. Okay. And then I convert this electron volt to joules. Why? Because maybe it is an easier way to calculate. So from electron volt, I'll just calculate, convert it to joule. To 1 electron volt is equals to 1.6 into 10 to the power minus 19 joules. And therefore 4 into 1.6 into 10 to the power minus 19 will do. And I think this answer will be 6.4 into 10 to the power minus 19. Is it right? Okay. And the second thing was, I'll just compare the value. So what was the wavelength of light? That was 496, right? Yeah. That wavelength of light was 496 nanometer. Okay. So I'll convert this to in terms of joules. So it will be hc by lambda, and it comes out to be 6.626 into 10 to the power minus 34, that is joule second, and multiplied by 3 into 10 to the power 8 meter second inverse, and then it will be 496 into 10 to the power minus 9, that will be meter. This meter cancels with this second to second inverse, and the answer what we'll get in is will be in joule. So I'll just use a calculator to For a faster calculation, yeah, so it will be, yeah, so my answer comes out to be 0.04 multiplied by 10 to the power minus 34 minus 8, it will be minus 26 plus 9. So it comes out to be 17, right? Minus 17. And then I'll convert, so it will be 4 into 10 to the power minus 19 joule. But this energy has come to be 4 into 10 to the power minus 19 joule, and our energy of the energy of this transition is quite higher compared to this energy, right? So then in this case, E2 to E1 is not our answer, so we have to find something else. So the second one would be, I'll try E3 to E1, but the energy is still quite higher, so we have to go for a lower energy transition. So we have two options. The one is 1.0 to 1.5, and the second one will be 1.5 to 4.0. So first we'll go from if you go from 1 to 1.5, so 0.5 electron volt will be the energy of transition, and if you convert the zero point 0.5 to joule, it will come to be zero point 0.5 into 1.6 into 10 to the power minus 19, and it will come to be 16 by 80, okay, and it will come out to be zero point 0.8 into 10 to the power minus 19 joule. Now it has become quite lower than what is the energy of our emitted beam. So this is also not the right answer. The third option I would like to go with is E3 to E2. That would be from 1.5 to 4.1, or that is E3 to E2. Okay. And what is the energy difference? That is 2.5 electron volt. So this particular thing what I have calculated is the energy of emitted or the output light, and what it should match with, it should match with the energy gap between two levels. Okay, and that is why we are doing this calculation. So first we did was of E4 to E3. Okay, this what we are doing, I'll write it down now again, a free from E3 to E2. So here the energy was 1.5, here it was that to minus, and this was minus 4.0 electron volt, and this is E3 to E2. So for this transition, it came out to be the delta E is equals to 2.5 electron volt, that to minus. So it will be minus 2.5 into 1.6 into 10 to the power minus 19. The answer will come out to be in joule. 2.5 into 1.6. Yeah. So the answer has come to be 4 into 10 to the power minus 19 joule. Okay. So this is the right answer what we were searching for. Okay. And as I said, there are different transitions. So different transitions which can happen are E2 to E1, E3 to E2, E4 to E3, E3 to E1, and that to E2, E4 to E1. But the more the energy gap is, the lower the wavelength would be. And anyhow, for our case, if we want to calculate for such type of questions, the energy, because we always calculate each thing in terms of energy, the energy of output beam. Output beam is what? Output beam is nothing but our emitted beam should match the energy gap between two levels. Okay, so this is the main principle. how we do the calculation for such type of questions. And therefore, okay, sorry, yeah, what we come on to the conclusion is, in this case, there are various transitions. See, from E1 to E2, E1 to E2, but no, this is sort of absorption. So there will be no output wavelength as such. Second is E1 to E3. E1 to E3 is also an absorption. The third is E4 to E2. So from E4 to E2, this is quite a higher energy difference. It will go to a lower wavelength. I think I said something wrong last previously, but E4 to E1, the more you go, the more the energy gap increases, the lower the wavelength will be. Then E4 to E3. E4 to E3 we had calculated, but its value was somewhat lesser, and therefore this was not our option. The what is this? Fifth number of option is E3 to E2, and this is the option what we got to be correct. I just hope this is the right answer. The energy gap was 2.5 electron volt, and when you convert it to joules, it exactly matches the value of 4 into 10 to the power minus 19 joule, and which is also equal to the energy of this. Okay, so for question number 3, this is the right answer. If you have any doubt in this question, you feel free to ask. Yeah, okay. So we'll go on to the next question. So first is, for a two-level system, the ratio of population of the higher and the lower energy states must be equal to or lesser than. So first option is 0.5, second is 1.0, third is 1.5, and the fourth is 2.0. Now what they're talking about is N2 upon N1. Okay, the higher energy and the lower energy state. Now, initially, what we discussed was, say this one is the population of N1, a lower state, and this is N2. Okay, and there is an equation which we came up to, and I think this means this question is more or less related to that same question. Yeah, N1 upon N2. Okay. So basically, if you want to say so, we'll go on to the solution of this question. Yeah. So I assume there is a long derivation of this process. If you of this question, if you want, I can just give a short, or I'll just write the equation which comes out at the last. Hello.
Yeah, I know the equation is like n2 by n total less than half.
Yeah. So
But
actually, what
yeah,
they're talking is they want that the ratio of N2 upon N1. Now, if I want,
yes,
yeah, so it should be now. If you want, the conclusion for that was that the for the overall stimulated emission to occur, the N total, which is a sum of
n1
N1
plus n2.
plus N2, right? And
Yes,
therefore, if you consider that both have equal values, and like for the N2 to be greater than N1, it should be greater than half, right?
yes,
Yeah. So if you consider the value of N2 upon N1, what they have given, the higher to lower energy state, suppose I take it to be like a ratio of, like the total comes to be 10. Okay,
yes,
because it will be easier to consider. And if I say the value of N2 should be Okay, it should be greater than half, so I take it to be 7 and the other I take to be 3. So what will be the value of n2 upon n1 then? 7 by 3, right? And just
Yeah.
so, okay, so it comes out to be 2.33, right? It should be greater
No,
than.
if we take the equation n2 by n total less than half, then if we instead of n total, if we write n1 plus n2, and
Yeah,
from that we can derive n2 by n1. But that time my answer is coming 1. But correct answer they say 0.5.
yeah, okay. So the ratio of populations they have told is equal to or lesser than they have told.
Yes. In that, their answer is zero point 0.5. That is for n2 by n total. That is less than half. That is zero point 0.5. But
Yes.
if I put n instead of n total, if I put n1 plus n2 and then I derive n2 by n1, in that case I'm getting 1.
Okay, so what did you put the value? Just tell me. Like n2 by n
n2
total.
by n total
So you
less less than half. So then n1 plus n2. Then I took the reciprocal in both sides. So it will become n1 by n2 plus 1 greater than half.
okay. So and
Sorry, greater than 2. And
okay,
then if you minus, it will be in the other side. So it will be n1 plus n2 greater than 1. If you take the reciprocal, that's the
it will
mistake
go
is
to the
happening.
RHS side, right?
Yeah.
And then you calculate n1 by n2. It should be greater than, okay, 2 minus 1 1. Okay, and then n2 by n1 should be less than, yeah. So for a two level system, the ratio of population of higher to lower, right? So
Yes.
now, leaving all these things, if you consider the higher should be greater than the lower, right? No,
No,
no.
n2
But
should be
in
less than 1.
ideal case, it happens. In the real system, what happens is,
N2 is always less than n1.
yeah. So if n2 is less than n1, then it should be equal to or less than 0.5, right?
No, if I say n2 is point, suppose if I take n2 is
0.25. Okay,
0.49
you take.
and n1 is 0.51, in that case we are getting some value which is more than zero point 0.5.
Okay, let's see. This is the ideal case. No, no, not an ideal case, but I assume this is an option. Okay, so if I take the total to be 1, the n2 I take to be 0.25 and n1 I take to be 0.75. And then I take the value of n2 upon n1. Okay, so it should be like 0.25 and 0.75 and it comes to be less than 1, right?
Which less than 1 also, it's in that case it is also less than 5. But if I take 0.49 and 0.51,
Okay. Yeah, this is the
then
nearest case. Okay. So 0.49 and 0.51. So in
yes,
that,
this coming 0.96.
yeah. So still it is 0. Acha. But it will never be equal to 1, na? Here they have asked equal to or lesser than. So it is lesser than 1.
Okay.
But it will never be equal to 1. It will always be lesser than 1. So among the option 1.5 and 2.0, they are never possible for a two system case if you consider the real system.
Yes, yes.
And if you
Okay.
consider n1 and n2, then 1.0 can be a situation, but I don't think that is achieved ever because then
Yeah.
n1 has to be equal to n2.
Yes. Okay, okay. I got it.
Okay. and
Yeah.
then it should be zero point
Point
0.5,
five.
I think.
Yeah. Okay. Thank you.
Okay. Yeah, yeah, sure. If you have other doubts in the other questions, you can also ask. And in the previous questions which I have solved, if you have any doubt in them also, you feel free to ask.
Oh, okay.
Yeah, okay. So is this question clear to you?
Yeah. Question number 4 is clear to me.
Okay. Okay,
I
I'll
have
just
another doubt in last question, but I will wait.
this one.
No, last. I mean the
Okay.
question number 11.
Okay, yeah. Okay, okay. So for a like within a short time, I'll just try to repeat this question. So in this question they have asked, for a two level system, the ratio of population of the higher and the lower energy states must be equal to or lesser than. But here they have not described like which type of system, or you can say the real system what they're talking about. And when we had studied, we got to know that n2 upon n total, where n total is the population of the two states. It should always be like it should be greater than the value of half, say. But what has happened here is, in this case we are not talking about this case we are talking about the real system, where we have to calculate n2 upon n1. Now if you take the normal condition where this n1 is the ground state and n2 is the excited state, in any case the n2 population will always be lesser than n1. Okay. And more or less the n2 will never be equal to n1 as well, or maybe it can. And if n2 is equal to n1, then the case would be that n2 upon n1 will come to be 0 point, sorry, 1. So what they want to ask is, since n1 is always greater than n2, if you calculate the ratio of higher energy state n2 upon n1, it will always come to be less than 1. Okay. And the second case is, it will never be equal to okay, yeah. And the second thing is, the two will never be equal. So okay, it will never be equal to 1. Okay, so it will never be equal to 1. So in all, it will always be it can be equal to 1, or it can be lesser than 1, but it cannot be equal to 1, so our answer would be 0 0.5. Yeah. So actually there is a bit confusion in these two, but I think what we are considering the assumption that is correct. So we'll go to the question number 5. The correct statement among the following is or are. So what our options are: the 3 level and 4 lasers are intrinsically CW and pearls respectively. The 3 level and 4 level lasers are intrinsically pulsed and CW respectively. Both 3 level and 4 level lasers are intrinsically CW, and both 3 and 4 levels are intrinsically pulsed. Okay. So what does this CW mean? This CW stands for continuous wave. And the pulse stand for, like, if you, with respect to time, if you plot the intensity for a particular time, it will increase like this wavelet, and then it will reduce to 0, and then it will again increase. So this is called the pulse form of laser. And if you talk about wave, it would be like continuous. Okay. So like it will not have intensity 0 with respect to the time. Now yeah. So the correct statement among the following is 3 level and 4 level systems are continuous wave or pulsed. So in order to understand this, first we'll go with the 3 level and 4 level type of laser. So initially what we discussed was a 2 level system where there used to be a ground state and there used to be an excited state. But what about this 3 level and 4 level lasers? So, what is the three level? Now, suppose there is a system of ground state, say 1, and excited state 2, but there is one more state which I consider to be 3 here, so at somewhat lower energy than 2. Now, in this case, what will happen? My system will absorb certain amount of energy, will reach to an excited state 2. After that, since the lifetime, I assume that the lifetime of this two state is very low, in the order of say femtoseconds. Okay, so I'll write it to be lifetime is low. Now from there, this reaches to a third state that is 3, and it has a greater lifetime. What has happened now? Suppose I stay say in this whole period of time, say within a fraction of second, if the molecules have excited from 1 to 2, they are, since the lifetime of this state is very low, they have reached to 3. But since the lifetime of this third state is greater than the lifetime of the second excited state, sorry, the molecule will reside in this excited state for some time, and then after it will radiatively emit. Okay, and this process from 2 to 3 occurs by a non radiative pathway. And now, non radiative pathways are those which do not involve the emission of radiation simultaneously. Okay, and those pathways which in which the some sort of light radiation is emitted, those are called the radiative pathways. This is non radiative pathway. This includes the vibrational relaxation, or you can say in the form of heat, the system loses its energy. Now, from that third state, it has come to the ground state. What we were want to know is whether this is continuous wave or pulsed. Now, what I want to say is this is a three level system. First of all, suppose initially the at time 0 the system has all the molecules in the ground state. Now, after some time, by the excitation, some of the molecules have reached to an excited state, and with this only, within some with further time, most of the molecules they have come and relaxed to this third state. Now, after getting this, after reaching the 3 with the stimulus, from 3 they reach to a ground state. Now, this may happen that this excitation, accumulation of population to the third state, and then simultaneous emission, this has happened for a cycle. But for again for this third state to be populated again, and then again the emission to occur, there maybe there you will need a fraction of time. So in this case, the pulse, or sorry, the laser light would be in the form of pulse. Why? Because this state may take some time to get populated, and therefore this type of laser, the three level system, will be in the form of pulse, which can be like with the respect to intensity, with respect to time, it will give a plot like this. Okay, actually this is like this has a single peak, a maxima, and the like then comes the decay. Okay, so this is what we talked about, three level system. And opposite, and in the other case of a four level system, what we let us consider, this is 1, this is 2, this is 3, and this is 4. Initially, all the molecules in the ground state they reach to an excited state 2. After that, through a non-radiative pathway, they reach to an excited to the other state 3. From 3, to the other excited state, that is say 4, and this process in this case is a radiative emission. And again, from 4 to 1 it relaxes through a non radiative pathway. I've written it to be NRP, and this is also non radiative pathway. Okay, and this is simply the absorption process. Now, in this whole scenario, let us think the case where one goes to absorb some energy of light, wavelength of light, reaches to a state, say second, to the first excited state, that is denoted by 2. With a non-radiative pathway, it comes to the third excited state, which is named as the 3. This is not the actually the third excited state, and from there through a radiative pathway it reaches to the 4, and this is the total cycle. I assume that this fourth excited state has a lower lifetime. Because of this lower lifetime, this fourth energy level will soon, within lesser time, it will come to this ground state through a non-radiative pathway. Now, anyway, since the lifetime, this has a longer lifetime, and this is a shorter lifetime. Anyway, from 1 to 2, since this is also a fast process, most of the molecules will reach and come to this third excited state. And after that, from 3 to 4 happens a radiative emission, and from 4 to 1 the molecules immediately, without taking much time, they reach to the ground state back. In this whole process, what we want to say is this radiative emission step, it will happen continuously. Why? Because anyway, from 1 to 2 and 2 to 3, this process is a fast process. So anyway, the population of 3 will always be greater than that of 4, because the 4 is decaying and coming to the ground state very fast compared to the third state. Since it has a longer lifetime, most of the molecules will stay in this third state rather than the fourth one or the second one, and therefore from 3 to 4 this radiative emission will occur continuously, unlike the first case, which was the pulsed one. So here they have asked about respectively, and 3 level and 4 level lasers. So the 3 level laser, which is a pulse laser, and the 4 level laser, which is a continuous wave laser. So our option would be the 3 level lasers are intrinsically CW and 4 level are pulse. This is not our option. The second option they have written is 3 level and 4 level lasers are intrinsically pulsed and CW respectively. Okay. So this is the answer for our question, I assume. And the other two also, we'll just discuss them. As I told, in this case, the three level system, this is a pulsed form, so 3 is pulsed and 4 level lasers are continuous wave lasers. Okay. There is one more option where they have written both 3 level and 4 level lasers are intrinsically continuous wave, although there can be cases where 3 level system is intrinsically continuous, is also continuous wave rather than being pulsed. But in this case, where you consider this kind of 3 level system, most of the cases the 3 level systems are pulsed only, they are not continuous wave. And both 3 and 4 level lasers are intrinsically pulsed, they have told. So this is also not the case, because 4 level lasers are anyway, they are the continuous wave lasers. Now since you have already gone through the week modules, can you give me an example of a pulse laser and a intrinsically continuous wave laser, or else I'll be discussing. Okay. So the example of the pulsed is a diode laser, and the continuous wave is any laser, that is Nd:YAG laser is also a continuous laser. Okay. Now, one more thing which I want to discuss here, that is an extra fact about the three level system. How can these three level be a continuous wave system? Okay. So for this, how can the three level be continuous wave? So if the lifetime earlier we were considering 1 and 2, okay, and this is the 3, okay. Now, earlier what we thought is this has a greater lifetime and this has a shorter lifetime. What if I exchange these two, or I say that the lifetime of second is greater and the third is shorter? If the lifetime of second would be greater and third would be shorter, we say that the process of absorption is not stopping. It is continuous. That is, continuously the molecule is absorbing some amount of radiation. Excitation from the ground state to the excited first excited state is happening continuously. And from this excited state of the second, which has a longer lifetime, continuously from 2 to 3, which has a shorter lifetime, the emission can occur, because anyway from 2 to 3 the emission can occur. Okay, so if I reverse the case where earlier 2 had a shorter lifetime and 3 had a greater lifetime, if I assume that the 2 has a longer lifetime and 3 has a shorter lifetime, okay, so since 2 has is continuously the pumping of sorry, or you can say continuously the excitation from 1 to 2 is going on, there will be no barrier from 2 to 3. Therefore from 2 to 3 there will be continuous uh, emission, continuous simulated emission occurring. So we can say that the three level system can be pulsed as well as three level system can be pulsed as well as continuous lasers. So first of all, I'll clear this area bit so that the right answer is, yeah. So our answer to this question is three levels are intrinsically pulsed and four levels are intrinsically continuous wave. This is our right answer. Um, do you have any doubt in this question?
No.
Okay. Now I'll proceed to the question number 6. In helium neon laser, in helium neon laser, both helium and the options for this are both helium and neon are energized directly by electrons. Helium is energized by electrons and transfer the energy to neon. Neon is energized by electrons and transfers the energy to helium. And emitted light of one gas is reabsorbed by the other. Okay, so I'll give a brief description about the helium neon laser, so that we can directly come up to the answer from there. First of all, helium neon both are the noble gases. Okay, and in this, what is the setup they do is, first of all, this is, just The setup is, here they put some like this is the gas chamber, or the you can say the gas cell, and then here comes the reflecting mirror, which is a totally reflecting mirror, and here is the partially reflecting mirror, and here is an high energy source connected to this compartment. So initially they provide a high energy source. Because of this high energy, the helium and neon both get ionized. From the helium and neon being ionized, say He to He plus and neon to Ne plus, they release high energy electrons, and these electrons also transfer this high energy to helium plus and neon plus ions. Okay, so this is the energy level diagram, which I have taken from the same lectures only. So what they have done is, say helium has the electron configuration of 1s2. From 1s2, the electrons are excited to 2s, and 2s excited triplet in the states, and this is the helium plus ion. Okay, and from this helium plus ion, the energy transfer occurs to the neon plus energy states. Okay, now what is the entire procedure of this? First, the helium and neon, they are ionized to He plus and neon plus, and second thing what they have taken is the ratio of pressures, partial pressures of helium is to neon is always taken to be 10:1. Okay, so if say I have taken the helium to be 1, the neon would be 0.1 or 2, so is to 0.2, and that too in terms of torr. Okay, the partial pressure. Now they have considered helium to neon laser, uh, where since the helium is in large quantity, it, although the reverse process can occur, but here we are considering the process which we want to consider for the working of helium neon laser. Anyway, since helium is in higher concentration than neon, so the energy transfer from helium to neon occurs. Okay, now which through this energy transfer itself, the neon which is in ground state, ideally it also reaches to a higher energy state, but this energy transfer from these two states comes to 2p5 5s and 4s. Okay, and what is this 2p5? Neon is a uh, noble gas, so its configuration, let's say it is 2p6, so in the Ne plus state it will lose minus 1 electron, and it will convert it to 2p5. Along with 2p5 there are the other states, which is 5s and 4s. So the energy transfer occurs from uh, this 2s state to 2p5 5s and 2p5 4s states. Also, the 2p5 4s energy is lower than 2p5 5s, and therefore, as you can see in the energy level diagram. Now, from this excited state, there are other states which are 2p5 4p and 2p5 3p. The energy transfer occurs. The second point to note is, depending on from which state to which state the energy transfer is happening, there are different wavelength of light which you can get from the helium neon laser. So here they have given three values. The first is 3391.3 nanometer. The second is 632.8 nanometer. The third is 1152.3 nanometer. Okay, so actually, if the higher the energy, the lower the wavelength. Um, see the high, yeah, since the wavelength value is quite high in this case, this is the least energy transition which is happening from 2p5 5s to 2p5 4p. There are 10 states of this energy, and this energy transfer, when occurs, it corresponds to the emission of 3391.3 nanometer. Actually, this is quite lower in energy. And the second one, which is of 632.8 nanometer, from 2p55s and to 2p5 3p. Okay, so this transition is somewhere which lies in the visible range. This transition lies in the visible range of light. The last one is 2p54s. Yeah, so the last one is 2p54s, 2p54s to 2p53p, and this corresponds to 1152 nanometer. This also still does not lie in the visible range of light, and therefore we have come to the answer, which is in the helium neon laser. First of all, actually this point is discussed previously only. Both helium and neon are energized directly by electrons. Okay, they both are energized, but the helium is energized by electrons and transfers the energy to neon. Okay, and since actually both can be energized, but since the helium is more in quantity, more in concentration, so the helium being energized by electrons transfers the energy to neon, and then neon is energized. So basically, since what we know is, yeah, so yeah. So this is the right answer for this question. The helium is energized by the electrons and then transfer the energy to neon. The reason for this is helium is to neon ratio is quite high. Like helium is almost in the ratio, helium to neon are almost in the ratio of 10 ratio 1. Although both are initially ionized to helium plus and Na plus Ne plus, and both are energized, but the energy transfer always occurs from helium plus to neon plus. Got it? So this is the answer for this question. Helium is energized by electrons and transfers the energy to neon. Okay. Now, is there any doubt in this question? Okay, your voice is not audible uh, to me.
I said no.
Okay, okay. Thank you. Okay. So I'll go to the question number 7. If L is the cavity length and n is the integer and lambda is the wavelength of longitudinal mode, then L is equals to. Okay, so this question is from the last part of our week 4 module. Actually, if in the laser cavity, what we say is, first let us see, this is a system, or you can say this is the, and this is, say, if I'm talking about ND-YAG laser. So this is the this is our source basically, and we need something which pumps, or this is a system which provides the energy to this NDAG component, which then emits light. Okay, so this emits light, which is which moves through, or which is emitted in all the directions. Okay, and here comes, there is the uh, reflecting mirror. So it is totally reflecting mirror. So I'll write it to be 100% reflecting mirror. and this is the partially reflecting mirror. Okay. Actually, what we want to understand will not be explained by this diagram, will be explained like, suppose I consider this entire cavity through which the mirror will through which the light beam is passing in the round like circles. Say it comes from one, say one, this point to this point, it again comes back, passes through the material, it excites the other or stimulates the other photons to emit, and then it reaches here. Okay. So how does the laser work is, suppose the two photons or three photons are initially coming out of this laser in the at from, say, at the initial of the process. After that, these photons will be released in this direction, they'll be reflected and will again pass through the same Nd:YAG laser. These photons act as a stimuli for the emission of photons from the other level. Say this, these and these two are the levels. From here, the radiative emission will occur, and these photons act as the stimuli. Therefore, suppose initially two photons are there, they will act as a stimuli to release more two photons, and this is how they will be again continuously going on through this system of 1 2 1 2, and the number of cycle it repeats, the more will be the the more will be the photons, amount of photons released. In all, there is multiplication in the number of photons of light of a particular wavelength. Now, suppose this I take as the cavity length. So, how I am considering the longitudinal mode in the direction of propagation of light? Suppose I consider these many. Okay, a single longitudinal mode which has a wavelength lambda. Okay, and L is the cavity length. So, this cavity length of this entire system is taken to be L, through which the light beam is passing on and fro, like to and fro. So, actually, this is a direct relation. If the cavity length is L and n is the integer and lambda is the wavelength, the relation that is the cavity length L should be n lambda by 2. So, it should be integral multiple of half of the wavelength. What it should be? It should be integral multiple of half of the wavelength. Got it? So, also there is one more thing that to note, that the n value should is not less than 1. It is always from 1 and can reach to infinity. Okay. Now, where n, what is the value? Okay, yeah. So, what if I talk about the n is the number of longitudinal modes? So, if you want to calculate the value number of longitudinal modes, if the length of the cavity is say 1 centimeter and the lambda is 400 nanometer, what if I want to calculate the number of longitudinal modes? So it will come to be 2 into L by lambda, and then we'll convert each to the same unit. So it will be 2 into L. Well, L was 1 centimeter. I'll convert it to meter, that is 10 to the power minus 2. And then 400 into 10 to the power minus 9, because each one I have converted to meter. So it comes to be 200. It is 10 to the power 2, so it will be 10 to the power minus 2 into 10 to the power 7. So it will be 10 to the power 5. So total n will be 10 to the power 5 modes. Okay. So if the wavelength of light is lambda and the cavity length is say L, it should have n lambda, and the cavity length should be integral multiple of the wavelength or vice versa. So this is a direct relation, and since in our first we'll take a look of at all the options. So first one was L is equals to n lambda, L is equals to lambda by n, L is equals to 2n lambda, and L is equals to n lambda by 2. So first of all, what we learned from this discussion was the L is equals to n lambda by 2 is the correct option for this question. The second thing, suppose I give you the, in all these options I give you the option L should be equal to 4n lambda by 8, then also the relation will come to be the same and it will come to be n lambda by 2. So in any way the expression is given, we have to find out the final value. Okay, so 2n lambda, often may people may get confused with this answer also, uh, may confuse this answer with the right answer, but the right answer would be n lambda by 2. That is the integral multiple of half of the wavelength. And second thing is this n, it is never 0, n is never equal to 0, and its value varies from 1 to infinity. Okay, and okay. So is there in any doubt in this question?
No.
Okay. Uh, Now we'll go to the question number 8. So, question number 8 states, in the semi classical treatment of radiation of matter with light, light is considered to be photons, it is considered to be wave, it is considered to be perturbation or non resonant. So, first of all, in the semi classical, in the classical treatment of light, the light is considered in not to be in the form of waves. Okay, but when you go to the like in the semi classical treatment, the light is considered to be as wave, and second thing as perturbation. Okay, so initially what was, when we were talking about let's say one state 1 and 2 and how the emission to occur, there is also some other definition to explain this condition of emission. They say that there is some disturbance in these two states which is responsible for the emission. What is that disturbance? That is the perturbation. Okay, so actually in this question, yeah, in this question there was only one choice, one correct answer, but in this case you will have two correct answers for this question. The first one is the wave and the second one is perturbation. In the classical treatment, light is not considered to be as wave. Okay, so in the semi classical treatment, light, the this part of the light is also taken into consideration. Okay, now, with this, do you have any doubt in this question? Actually, this is a theoretical question. We means,
Yeah,
uh,
I just want to know what do you mean by non-resonant?
okay. Actually, this I do not know, but actually, this option amongst these non-resonant is not related to this. Like this is just an option given. Like we do not have any explanation of how light is considered to be non-resonant. This is just one of the options given, which is not correct. So if you talk about photons, light can be considered. Light is also considered as photons, but non-resonant. You should not go on with to this option. This does not even lie in this case of the treatment. Okay,
Okay.
yeah. So the question number 9 is, among the following lasers that has or have fundamental wavelength in the visible range is. Okay. So first of all, initially in the first options, we had learnt about the helium neon laser in the earlier questions. Although I told you there are three different values, the 3391 point something nanometer, the second one was 623 nanometer approximately, and the third one was light in the range of 1100. See, I think the what is the exact value for that? Yeah, this is the 1152.3. So, actually, if you want to consider the answer, you have to consider this also as the right answer. Although it has two wavelengths which do not lie in the visible range, this particular one lies in the visible range. So first of all, one of the answer would be helium neon laser. Since one of the wavelengths, which is from the transition of say the it was from yeah from 5s to p5 5s to 2p5 3p, so this transition corresponds to the visible range of light. The second one is ND-YAG laser. Okay, so actually in case of ND neodymium and YAG is YAG stands for yttrium, aluminium, garnet. Okay, so this in case of ND-YAG laser, the fundamental beam which it emits is of 1064 nanometer. Okay, but what happens is with the help of certain second harmonic generating materials, this 1064 is converted to say 532 nanometer of light. Okay, or you can say the lambda is converted, or the wavelength is done half and the frequency is double. So frequency doubling occurs in this case, and if um, and what you get after frequency doubling, that is that lies in the visible range of light, but the fundamental frequency does not lie in the visible range of light. It lies somewhere far in the IR range. Okay, so since here they are all asking fundamental wavelength, this will not be our answer. Okay, and often I think people will get confused in this case, because anyway what we study is the 532 nanometer also, but we need to know the fact that the fundamental for this case for ND-YAG laser is 1064 nanometer and not 532 nanometer. Okay, so this is not the option. For the titanium sapphire laser, actually, earlier we had discussed that the titanium sapphire laser is quite a good laser, which emits a high intensity of laser beam, and that too it continues from the visible to the IR range. Okay, so that is why the titanium sapphire laser, it also emits in the visible range. It's fundamental, and you can consider like its emission is in the range of 780 nanometer. Okay, and then the last option is ruby laser. So ruby laser is what is ruby laser, do you know?
It's a three-state laser.
Yeah, and like actually it is
It will be
the
in visible.
with
600.
with aluminium and chromium, right, in
Yes,
ruby.
yes, yes.
Yeah,
No, I think aluminum oxide or something.
yeah,
Al2,
yeah, it is
Al2.
Al2O3 with Cr plus 3, chromium in
Okay.
plus 3 state. So ruby laser is also a laser which emits in the visible range. Actually, I think from the exam point of view, this question is quite important, because generally maybe this question can be asked in your final answer exam. And the ruby laser, it emits in the range of 694 nanometer. So if you want to
Yes.
write the details, I'll just clear this page so that you we can just write the conclusion for this question. Okay.
Okay.
Yeah, okay. So I'll just write the what is the fundamental frequency of these respective lasers. Yeah. So for helium neon laser, what we discussed that lies in the visible range was 632.8 nanometer. The second what was titanium sapphire laser, for that it was 780 nanometer. For ruby laser it is 694 nanometer. Okay. The other thing is, along with helium neon, in the helium neon laser, the other two wavelengths are 3391.3 nanometer, and the other one is 1152.3 nanometer. Okay, and these are the other two wavelengths which you can get using the helium neon laser, based upon the electronic transition which is based upon the transition which is occurring. And also I'll write for this in neodymium YAG laser, ND YAG laser, that is to be 1064 nanometer. Got it? So, is there any doubt in this question? Actually, this is just the theoretical question, also, again, and you have to just remember these values, memorize these values, so that it will be helpful in your exam. Now, is there any doubt?
No.
Okay. So, we'll go to the question number 10. A mode locked laser has a broad spectrum, is absolutely monochromatic, is a pulsed operation, is CW. Okay. So, first of all, um, uh, yeah, for this I have just, this is a short summary of what is mode locking. So, in the mode locking, what they do directly is the anyhow by any modification, the phase difference between the each modes is maintained to be zero. Okay, so suppose these are the different longitudinal modes which have a different value of wavelength. Okay, say this if you see the picture, you will get to know which has a greater wavelength and which has a shorter wavelength, right? Can you just tell me between these two, which has the longer wavelength and which has the shorter wavelength? Yeah, basically, if you consider this as the complete wave, which one crest and when trough, the distance covered by a single wave is a wavelength.
Yeah,
So
yeah, yeah.
yeah, so from this figure, at least you can say, see this wave is completed in a short distance compared to this wave. Okay, and if you count one, two, three, only three waves, or you can say one, two, three, four, five. Five waves are completed in this, and in this only three. So basically, pictorially only you can say that this has a lower wavelength and this has a high. Sorry, this has a lower wavelength and this has a higher wavelength, right?
Yes.
Okay. Now, oh, okay. I just want to say is, in the mode locking thing, actually the whole calculation is a bit complicated. But in short, if you want to learn, the phase difference between each of these modes is taken to be zero. Anyway, it is modified and taken to be zero. Now, when you see, suppose this is at a point of time where they come to be like, see, they are in all in the same phase. So at this point of time, say I open the if I consider a shutter I have opened, so this phase just is emitted, and they are all in the same phase, and after a certain particular point of time, again I just open the shutter and close. So in all is at when they all are in the same phase and they give a maxima. Okay, the resultant is a maxima, and this whole pulse in the form is in the form of this wave. Okay, at L by C. And if you see, this will repeat itself at L by C and then again by 3 LC, and then again simultaneously if I draw 5 L by C, again you will see that they are again in the form of, like, they give a pulse, and that is like this. So basically, what mode lock the laser is, mode lock laser is not absolutely monochromatic. This cannot be the answer, because when you see, they have a different value of lambda. Okay, so a mode lock laser is not absolutely monochromatic, so this is not our right answer. Second thing, it is a pulsed operation. Coming to this option, it is a pulsed operation. So yes, if you consider this of intensity as a function of time, uh, you will see that the mode lock laser will be in the form of pulses, sudden like with respect to time the intensity will reach to a maximum, then again come to zero, and then will repeat itself at regular time intervals which are fixed. Say in like our pulse has repeats itself, sorry, our pulse has a time of 200 femtosecond. It lives for this particular time of 200 femtoseconds, and it repeats itself, like, okay, you can say 80 megahertz if it has a frequency. So you can get 80, or you can say 80 into 10 to the power 6 per second. This will be the repetition rate. Okay, so this much time the same will be repeated in a single second. In 1 second it will be repeated this many times. Okay, so, and also if you want to calculate the intensity is just the square of the amplitude. And if you want to calculate the time, then it will come to be 12 by c, and what you have been given here tp. So tp is the time period of a given pulse, which depends on the 2l upon cn. And one more conclusion which I want to deduce from this relation is, see, TP is the time period for a pulse, so 2L depends on 2L upon Cn. Now in this, all the factors L, the cavity, the length of the cavity L, C, which is the speed of the light, all these are fixed. So L is the length of cavity, C is the velocity of light, and therefore n is the number of modes. Okay, so the more will be the number of modes, the less will be the pulse time. Okay, the time of a single pulse. So this concludes that if you want shorter pulse, you should have more longitudinal modes. Got it? So this will be the answer. And with this, um, in the mode log laser, that is a pulsed operation. This is not a continuous wave. This is absolutely monochromatic and has a broad spectrum. Why? Because it is not monochromatic with a single wavelength. It has a wavelength, like it has, maybe you can say, a range of wavelength. Okay, so it gives a broad spectrum. Now, do you have any doubt in this question?
No.
Okay. So with this, we come to the question number 11. I suppose you had doubt in this question, right? Hello?
Yeah, yeah. In this question, I had doubt, but
Okay.
that was I think that time it was no options. Only you have to write the value.
Oh,
That's
okay. Okay, okay, okay. Yeah, so anyway, we have to solve this question. For an amplified laser, the power is taken to be 1 watt. And if I say what is joule per second? Okay, and it would be better if we solve this entire question in this unit, because it will be easier to solve. The repetition rate of each pulse is 1 kilohertz, or if I write in terms of hertz, it is 10 to the power 3 hertz, right? Or you can say 10 to the power 3 second inverse. And what is repetition rate? Which means if you talk about 1 second, it it repeats itself 10 to the power 3 times. Means 1000 times the laser, 1000 times the pulse you get in 1 second, right? And then the pulse duration for each, like a pulse, for say if it is the plot of intensity with respect to time, for what time does this pulse survive? So it lives for 100 femtoseconds, a short pulse. And what is the wavelength of this amplified laser? So wavelength of this laser is 800 nanometer. What are the other things? Say the energy per pulse. Okay, so if the power of the amplified laser is 1 watt, and in 1 second you say it repeats itself 10 to the power 3 times. Okay, so how we can calculate the energy per pulse? I'll just give a basic mathematical relation, and it you will find it easier to be solved. Energy per pulse, so energy is in terms of joules. Okay, what if I write, see, what if I write the power that is in joule per second, and then the repetition rate, how many pulses, like 10 to the power 3 pulses per second. So if there are 10 to the power 3 pulses per second, and per second the amount of power of that pulse is in joule per second is 1. So if I uh, just cancel them out, so the total energy in 1 second was this much, and the total number of pulse for 1 second was this much. And if I do divide them, I'll get energy per pulse, right? Because the repetition rate, what does it means? Pulse per second. Okay, and this is energy per second. If I divide, the 2 seconds will be get cancelled, and I'll get energy per pulse, and therefore the energy per pulse would be, say, 1 joule second inverse whole upon, what is the repetition rate? 10 to the power 3 second inverse, means pulse per second. Okay, here in order to describe this, I'll write it as pulse per second, and it is joule per second. Per second will be cancelled, so joule per pulse, or the energy per pulse will you will get. Okay, so anyhow the relation, the answer comes to be 10 to the power, or here I'll write it comes to be 10 to the power minus 3 joule. Okay, so energy joule per pulse. Is there any doubt in the solution of till now?
The question in the assignment was to write the value of energy per pulse. So I got the value 0.001, and but they told to write up to 4 decimal places. So I wrote 0. Okay, okay. Yeah, yeah, got it. Actually I now realized the mistake. I actually put the decimal point wrong. That's why I didn't get the marks.
Okay. If you want to write it up to 4 decimal places, you can just write
Zero.
0.0010, right?
Yeah,
So it will be clear.
yeah, I
Now
got it. I
the
got it.
okay. Is it clear now?
Yeah.
Now the second thing. What they have asked, number of photons per pulse. Actually they want us to calculate the answer, and amongst these there's suppose number of photons per pulse, energy per pulse, radiative power per pulse. So we have to calculate this and just tick the right answer if our answer what we have calculating is matching with what they have written. So number of photons per pulse. Okay, so suppose now how to solve this question. Suppose the total energy per pulse will be the, like you can say, there are n number of photons in one pulse. Okay, and say the total energy per pulse, what it will be, we have calculated it, right? Energy per pulse we have calculated now, that is 10 to the power minus 3. And then what if I say energy per photon? Okay, so I'll write it on a fresh page. Yeah, so energy per pulse, what is it? 10 to the power minus 3 joule. Now in one pulse there can be n number of photons, right? And since the wavelength we are given is 800 nanometer, we can calculate the energy of one photon. And energy of one photon will be hc by lambda, and it will be 6.626 into 10 to the power minus 34 into c, what is 3 into 10 to the power 8. This is joule second, and this is meter second inverse. Okay, so this 2 will be cancelled, and in the it will be 800 into 10 to the power minus 9 meter. Meter to meter will be again cancelled, so we are left with 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 upon 800 into 10 to the power minus 9. And therefore the answer will come to be, actually I have calculated this before only, so the answer will come to be 4 into 10 to the power 15 somewhere. If you just want to cross check, you can just use a calculator and cross check fast. Okay, I think the 6.626 into 3 comes to be 8, 7, 8, and 19, 19.878, right? 60 is 81, yeah, upon 800. And if you solve these powers, 10 to minus 26 plus 9, 10 to the power minus 26 plus 9 comes to be 10 to the power minus 17, right? Yeah. And if you divide this whole, you will get, okay, just a second. Is there any problem in the power? Yeah, okay. Yeah, no, 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 no. It will be solved later. So when you calculate it, 878 divided by 800, 2.4 into 10 to the power minus 2. So it will be 2.4 into 10 to the power minus 2 into 10 to the power minus 17. So it will be 2.4 into 10 to the power minus 19, right? And this is in joules. Right? So energy per pulse is equals to number of photons per pulse multiplied by energy of one photon. If I want to calculate, what I was asked here is number of photons per pulse. So I have to calculate this number of photon per pulse is equals to energy per pulse whole upon energy of one photon is equals to 10 to the power minus 3 whole upon energy of one photon has come to be, okay. Okay, yeah, there is a mistake. If you want to calculate, okay, no, 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 into 10 to the power 2 it was, and it has reached 10 to the power minus 1. Yeah, so the whole answer will come to be 10 to the power minus 19 into 2.4, right? It will go up there and it will come to be 10 to the power 16 into 1 divided by 2.4 will do. So it comes to be 0.41. So here I'll write it 4.16 into 10 to the power 15, right? So this is number of photons per pulse, right? So here comes, we have solved our second option also, and if I remember here also the same option was given. It is almost equal to 10 to the 15 photons in one pulse. So this is also quite a large amount. This is correct answer and this is correct answer. Now what we have to calculate is radiative power per pulse. Okay. So with the help of units only we can solve this question. Okay. Radiative power per pulse. What is it? See, If you want to calculate power, it is in joule per second, right? And what we are given here, radiative, yeah, joule per second. Okay. So energy of one pulse is equals to, yeah, okay, energy per pulse is equals to 10 to the power minus 3 joules. Okay. And for how much time that pulse is there, that is for 10 200 into 10 to the power minus 15 seconds, right? And therefore if it goes up, it comes to be 10 to the power 12 and into 1 upon 200, right? And if you do it 1 upon 2, say it is 0.5 into 10 to the power 12 upon 10 to the power 2, so it will come to be 0.5 into 10 to the power 10, right? And since it is joule per second, yeah, we'll write in terms of watt. So the radiative power per pulse, if you want to calculate, actually that will be the energy per pulse upon the time of pulse it takes. Okay, yeah, exactly. Yeah, this I did wrong. Actually, this was not 200, this was to be 100. So it will be 1. It will also be 1. So 1 upon 1, it comes to be 1 into 10 to the power 10. Okay, so the answer has come to be 1 into 10 to the power 10. Let's check what is it, which of the two. So this is also the right answer, not 10 to the power 8, but our radiative power per pulse has come to be 10 to the power 10 watt. Got it? So here we have solved all the questions of this week for module. I would like to ask you if you have any doubt in the all any of the questions which we have solved.
No, no doubts.
Yeah. Okay, so Uh, for this session, all the questions are completed. Thank you so much for joining the session. With this, I, I just want to end the session. Thank you so much for joining.
Thank you.